Chapter 8 will be the inverters topic. So we have discussed so far, we discussed DC to DC converters. We discussed AC to DC rectifiers, right? We discussed AC to AC voltage controllers. I would not say power converters because there are many topologies. I think you guys are going to be exposed to a lot of the AC to AC converter topologies. There are many types that we will not discuss here or here actually, but the last sort of area that we want to discuss, or converters that we would like to discuss, are the DC to AC converters, and these are called inverters. Right? We discussed a little bit about inverter operation in our rectifiers topic, and this was a very special type of inverter. I mean, it's a thyristor-based inverter. I mean, they are used typically at very high powers because thyristors are very rugged devices that you can use at high power. So some very high power drives are driven by inverters that are thyristor based, right? Very high power, like 20 megawatt based drives, etc., etc. We will be talking more about PWM, pulse width modulated DC to AC inverters in this section, in chapter 8. Okay, so the objective is, of course, we would like to create as nice of a sine wave as possible. That's the final objective. We will be skipping. I know this looks like a lot, but we will be skipping a lot of stuff, and a lot of this will be things that we have to know. Just draw the circuit, draw some waveforms. So it's something. It should not be too much of a problem. Where do we use these inverters? Again, anytime we want to convert from DC source to an AC load, like adjustable speed motor drives, uninterruptible power supplies, hybrid vehicles. There are many applications of inverters. One of the simplest inverter topologies is something you are actually building in the project, which is the full bridge inverter, right? So you are building that with the purpose of creating DC at the end, right? But in the intermediate stage, you're creating high frequency AC, right? So you have our full bridge inverter. Looks something like this. You have your DC power supply here. Again, remember our trick that we talked about here. The way I would like to represent this is the same way I discussed the DC to DC converters as well. So I can represent this full bridge converter using this simplified representation that I discussed when we discussed DC to DC converters. Right? I have a pole here, or an arm here that's moving between these 2 points. And I have one here that's also doing the same. I just happen to have the same DC voltage applied to this arm and same DC voltage applied to this arm. The other thing is we always said that here across these switches, which I represented using this sort of arm with 2 contacts, right? Across them, I always have a fixed voltage, right? A stiff voltage. Remember we said in the buck converter, the stiff voltage is the input voltage. In the boost converter, the stiff voltage is the output voltage. In the buck boost converter, that stiff voltage is the V input minus V output, right? Here, I have the same thing. I have a stiff voltage here. That's always equal to this VDC, or the V input voltage. And at the output, I always had in the buck, or the boost, or the buck boost, I had the switch current going through an inductor, right? And it's the same here. I can draw this as half the inductor here, half the inductor here. They're in series anyway, right? And then this is my load for my inverter. This load can be a resistive load, so I can put this load here. It's coming. There's an inductor here, and I drew an inductor here, and then I can draw a resistor here, and maybe I put a capacitor as well. I can, right? Or maybe not. Right? Whether or not I put a capacitor will depend on how much ripple voltage I want to maintain across my load, right? So it's up to us later to decide if we put a capacitor or not. But if I want to select the switches that I put in here, I can go back to slides of the first chapter, right? The first chapter slides. What do I see here? current is in this load, I want to create AC current, right? I want to create current that is going to go into this node or out of the node, right? So it's going to go into this node or out of this node, right? But the voltage doesn't change polarity, right? So if we go back to this chapter 1 slides, that table that we had with how to select switch architecture, right? I have current here, positive, and current here, negative. Voltage is only in one polarity, right? My voltage here does not change polarity, right? My voltage is always in the same polarity. My current is changing, is either positive and negative, right? So I have to consider this architecture or this selection of devices as well as this selection of devices, right? So I have to find a way to combine these two, right? So how can I combine these two? You can go about it step by step. I want to combine the top two switches either in series or parallel. I want to combine the bottom two switches either in series or parallel. That's the only options that I have. If I take this switch and put it in series with this diode, I cannot do that because this switch is pushing current in one way and this diode is pushing current in the other way. If you put them in series, then you will have a switch here and a diode here. This wants to push current this way, this wants to push current this way. It will not work, right? So the only way to combine these would be to put the switch and the diode in parallel. If we do that, then we can allow current to flow this way in a controlled fashion and this way in an uncontrolled fashion, okay? But at least I can have current flow in both ways. And I have to make sure that in this reverse direction, there's another switch that allows me to control current flow in that direction, right? And that, if I do that, then I have controlled current in all directions, right? So that's the objective here. So now I can take this architecture that I came up with here and substitute it with devices if I want to. Before doing that, let's just see what's happening here. So this is V inputs. If I have this top arm connected to this node 1, 2, 3, 4, arm this arm on the left and arm on the right, the arm on the left connected to node 1 and the arm on the right connected to node 4. What's the voltage across my load? What's the voltage across my V output? Exactly. So if I have this arm connected to point 1, this arm connected to point 4, I've taken this load and placed it across Vn. How about if I take this arm connected to point 2, take this arm connected to point 3? What is the output across what is V output equal to? Is it Vn or minus Vn? You flipped it, right? So initially you had this case. This is V output.
You said you had two switches in there that control the current, right? Won't allow it back feed.
No, these are now ideal switches. For now, no. There's this is an ideal switch. This is just an arm that's flipping now. So when I had this arm connected to point 1 and this arm here connected to point 4, this was how my circuit looked like, right? And now if I now make this arm connected to point 2 and this arm connected to point 3, then the circuit would look like this. Current here was flowing this way. How about current here? The opposite way, right? So in one configuration I'm putting V input, in the other configuration I'm putting minus V input, right? If this is the polarity of V output, I flip the polarity of V input across it, right? So I have V input or minus V input. Do you agree? Okay. Another way to look at it How about if I do this? How about if I connect this arm to 1 and this arm to 3? What do I have across my V output? This arm to 1? Yeah, I would have 0. How about if I have this arm connected to 2 and this arm connected to 4? 0. So this converter topology allows me to get an output voltage. V output is equal to V input, or minus V input, or 0. Right? So I can get 3 levels of output. Okay? I can think of this in a different way. That's something more like what we've been discussing in DC-DC converters, right? So if I have this configuration, just this half of it, just looking at half of this thing, okay? This is operating with a duty cycle of D1, right? And this is my V input. We said that the average voltage I see here is always going to equal what? What's the voltage I will see here? It's either V input or no, 0. This is 0, my reference, or and this is V input. So the voltage here is going to be between 0 and V input, 0 and V input, 0 and V. So its average value is going to be between 0 and V input. But what is it equal to? In terms of D1? Exactly, duty cycle times? Exactly, so it's equal to duty cycle times V in. Right, so I have duty cycle times V in coming from this side. Right, I would like to look at V output. If I want to look at V output, I have V output here. V output is I want to know what my V output is equal to. Then I have to look at the voltage here minus the voltage here to see what my V output is, right? So now I looked at the left-hand side. My voltage is D1 times V input. Assume now that I don't allow for this 0 state. If I don't allow for this 0 state, then I'm always going to operate with how? I'm always going to have this arm at 1 and this at 4. Or this at 3 and this at 2. I will never have this 1, 3, and 2, 4 configuration, right? So let's now, for now, just forget about this 0 operation. If I do that, that means I'm operating this other side of the other side of the converter. So let me draw the other side of the converter here. Here I can draw the same V input across it, right? And here. I don't want to know what my voltage here looks like. This is same V input, right? So what is the average voltage here? What does that look like? Exactly. 1 minus D1, which is the same duty cycle, because I said that if this is the top, this is the bottom. This is the bottom, this is the top. So they're opposites of each other. So for the switching period, if this is D1, this is 1 minus D1. It's 1 minus D1 times same V input, because they're the same. They're the same, right? They're connected to the same DC input, right? So on one side I have D1 times V input. The other side I have 1 minus D1 times V input. So what is V output? V output is the difference between the two. So V output is equal to D1 times V input minus 1 minus D1 times V input. So it's equal to what? D1 V input minus 1 V input plus, right? D1, right? So it's okay. So 2D1 V input minus V input, right? Or V output is equal to what? V input 2D1 minus 1. So if duty ratio is equal to 0, what's my V output? Minus V in, exactly. If duty ratio is equal to 1, What is my V output? V in. Right? So my V output will range between minus V in to V in, depending on the duty ratio, which confirms what we were talking about here with this flipping business. Right? So you know you can now derive it easily, and we can do this for the half. So this is called the full bridge converter. The voltage, the range of operation, range of output voltage for the full bridge inverter is minus V input to V input, right? That's because I chose these to be complementary, right? If I am to include this zero operation, right? How will I write this? How will I write this? Can I write this as 1 minus D1? No, I will have to write this as D2, D2 times V input. And then the output voltage will be, you know, D1 times V input on this side, minus D2 times V input on this side. So the output voltage will be V input D1 minus D2, right? And in this case, if D2 is 1 minus D1, then I will operate only between minus, I can only operate between minus V input and V input, right? If I want to get zeros, I can make it 0. I can make these two duty ratios the same, right? If I make this 0.5 and this 0.5, then I can get a 0 as well, right? If D2 is 1 minus D1, I will operate between these 2 points. If I want to get the zeros to function, then I can operate in this fashion. What is the benefit of the zeros or not? We will talk about that next time. But I just want you to get a feeling of the operating range, and then we can do the same thing for the half bridge inverter. There's something called the half bridge inverter topology, and the half bridge looks like this. These are two capacitors, and this is my same representation. So this is operating with D1. What is the voltage here? Average value? V in times D1. What is my voltage here? This is the capacitive voltage divider. So this is V input here. This is V input over 2. Two capacitors across the DC supply. It's a capacitive voltage divider. This will be charged to half. This will be charged to half. So my output voltage now is equal to what? V in times D1 minus times V in over 2, right? This is my output voltage. I'll take output voltage between these two nodes. We saw that with this topology, I can have a load here. Let's assume it's a resistive load in this case. For a resistive load, if I turn on switch 1 and 2, I'm placing VDC across, this is my V output polarity. So my V output polarity is always fixed. So if I'm turning on 1 and 2, V output is equal to VDC. Right? If I'm turning on 3 and 4, V output is equal to minus VDC. I flipped it, right? So this is one way to operate these converters, right? So you just turn 1 and 2 on, and then turn 3 and 4 on. 1 and 2 on, turn 3 and 4 on. And that's what you're building. You're building that after the 12-volt battery charger, right? You're building a high-frequency AC converter. That's what you're doing, right? This is AC, this is not DC, right? Why are you doing that? You're doing that because you want to boost the voltage. You want to use a transformer because you want to boost the voltage from 12 volts to 180 volts. And you cannot use a regular boost converter because we saw the limit on boosting ratio is what? 4 times, for example. So from 12, you cannot boost to 180 volts. No way. So what's the solution? The solution is always a transformer. AC, but transformers do not allow you to translate DC voltages. They only allow you to translate AC voltages, right? The other solution is you can use 2 boost converters in series, right? If you boost 2 boost converters in series, so 12, you can multiply this by, let's say, 4. What do you get? 48. Multiplied by 4. No, it's closer to 200, right? It's 200, 200 minus 8, right? It's 198, right? 192 volts, right? So you can get your 180 volts. Sure, great. But then you have an efficiency here and an efficiency hit here. What's the total efficiency now for your DC stage, for your boosting stage? If this is, let's say, 90%, and this is 90%, your efficiency would be 0.9 times 0.9, 0.81. So 81% efficiency for the boosting stage. So this is one way to do it, right? Another way to do it is what you're doing in the project. What you're doing in the project, you have a full bridge inverter that you are creating a high frequency AC waveform from. This high frequency AC waveform, is it a nice, beautiful sine wave? No. And I don't care for it to be, because I'm going to rectify it afterwards, right? In your case, in the full bridge DC to DC converter, when you make a full bridge DC to DC converter that has a front end, basically, which is a high frequency DC to AC inverter, you don't care about the frequency content. But if you do the Fourier series for this, what will you find? You will find a lot of harmonic content, because it's a square wave. A square wave will have, again, if you go back to our Fourier series, here, this is the Fourier series for the square wave. V of t is equal to 4 V maximum over pi. All of these harmonics, first, third, fifth, seventh, it will contain all of these harmonics. Do I care? In your case, in the case of building a DC to DC converter, which you're going to take this waveform and rectify after that, you don't really care. You're not taking this into a load and looking at the power factor or the power transfer or whatever, because you're going to convert this to DC. When you convert this to DC, it's going to look like a nice DC waveform at the end, right? So you're going to rectify this. It's going to look like a DC waveform at the end, but you get the benefit of being able to go through a transformer by doing this, because you have an AC waveform. You can push that to a transformer. If you put DC across a transformer, the winding will not generate back EMF to oppose the voltage that's being placed on it. If there's no voltage to oppose the back EMF, if there's no back EMF voltage generated to oppose the voltage that you're placing across the winding, you place a voltage across a winding here. If this winding is not going to generate an opposing back EMF, meaning will look like this, having a voltage source in series, that's the equivalent circuit of a back EMF voltage developed across the winding. If the winding is not going to do this, then what's going to happen? Then you're placing a voltage source across a piece of wire, basically. So the resistance of the wire will limit the current. That's it. So you're going to be pushing a huge amount of current through. Pushing a huge amount of current through, you saturate the transformer. It's useless. You're not building a transformer anymore. You're building a heater, right? So only when the winding is able to generate the back EMF, and when is it able to do that? When you push an AC waveform through it. E equals, the back EMF is equal to N d phi by dt. The back EMF voltage developed across any coil is equal to number of turns multiplied by d phi by dt, the time varying value of flux, right? So it has to be an AC component, time varying component, to be able to push it through a transformer, right? So you do this in your circuit, right? After that, you push it through a transformer and rectify it. The classical rectifier that we studied, the diode rectifier, the full bridge diode rectifier that we studied at the beginning, right? No problem. This is great. And the equivalent circuit to what you guys are doing is the same as what I've been talking about, right? This is, at the end of the day, your transformer, right? It has, what's the model of a transformer? What does the model of a transformer look like? It has a leakage inductance and the leakage and the resistance of the winding, then ideal turns ratio, and then the leakages on the secondary side. And then if you want to consider the magnetizing branch, you can consider that as well, right? From 338, this is the equivalent circuit of the transformer. So there is an inductance in series as well. So same thing, I have my two switches, have a voltage across them that is fixed. And my output is going through an inductor, right? Nothing changes. All the power electronics topologies are the same. Always the two switches that are operating complementary have a fixed voltage across them. And between them, then there is an inductive current at some sort. You don't. It can be a transformer. It can be a big inductor. It can be a small inductor. It depends on your circuit's operation, right? So anyway, so you have these this inverter now that is creating this V output that is either minus V input or V input, right? If you are operating it in a complementary 1, 2, 3, 4, 1, 2 together, 3 and 4 together, right? And we operate with a duty cycle, a fixed duty cycle, right? If you go ahead and have a fixed duty cycle, but here we're operating. What's the switching frequency that we're operating at? What's the relationship between the output voltage frequency and the switching frequency? This is the frequency of the output. Okay. This is my output waveform, right? It's either Vin or minus Vin. When 1 and 2 are on, it's Vin. When 3 and 4 are on, it's minus Vn, right? So this is my period. So what's my switching frequency for operating an inverter in this fashion? What's my switching frequency? It's equal to the fundamental. It's equal to the output frequency, right? This is my output waveform. I'm operating switch 1 and 2 here. Then I'm operating switch 1 and 2 here. Then I'm operating switch 1 and 2 here. Right? So what's the switching frequency of switch 1 and 2? It's the same as the output frequency, right? It's happening one time every switching period. One time every switching period, right? So it's the same as the output frequency. You agree or not? Guys, come on. Huh? Why not half? No. No, I mean, remember this is a waveform. It's happening. I have a pulse here. Pulse here. What is the frequency of this waveform? You look at the period. And this is the period. So Fs is equal to 1 over the period. Right? It doesn't matter if this is this wide or is this wide. Right? Does it matter? It's turning on and off during a period. That's the switching period. It's turning on and off one time during this switching period. So what is the switching frequency? It's 1 over the switching period. Right or wrong? No, this is a question that I need an answer for. Yeah. Yes? You're not convinced? Yeah.
I don't get how it's the whole period. Like switching what is the switching frequency in this diagram?
Switching frequency is 1 over the switching period. So think of, okay, you take 4 classes. Does it matter? You take 4 classes a day. That's your frequency of classes. Does it matter how long the class is? Right? So this is happening. You're turning on the device and turning it off once every period. Once every period. This is my switching period. Right? The turn on duration. You're confusing duty cycle now with the period. Right? Your duty cycle is the time on over the time on plus time off. Or this is now the full period. You're confusing both now together. So I'm not asking for the duty ratio, I'm asking for a period, right? Or the inverse of that is the switching frequency. So how fast am I switching devices 1 and 2? I'm switching them one time during this period. So their switching frequency is 1 over this period, right? So this is the frequency of the output. So if I'm supplying a 50 hertz or a 60 hertz system with this inverter, I can, right? Would it be a problem if I plug this computer into this outlet that is being supplied by an inverter that's feeding a waveform like this? Maybe. It depends on the input specs of this. If the input of this PC is nothing but a full bridge rectifier, no, it doesn't matter. the input is a full bridge rectifier, if it's taking this AC voltage and just rectifying it, it does not really matter at all. It does not really matter at all. If it's a different thing, if it's something, if it's a circuit that's intelligent enough to detect, okay, I have too much harmonic content, so I'm gonna be just heating up my board without transferring real amount of power to the system, right? Lots of current, lots of voltage harmonics, for example, or if this is a current waveform, lots of current harmonics with no power transfer. Then it's a different problem. Some equipment will tell you, we allow for distortion, voltage distortion of a certain amount. You exceed the voltage distortion, I will shut down. It's like the thermal shutdown we talked about the other day, right? So, but yeah, you can plug this, you can take this inverter and supply an AC load, and no problem, it will work. And the benefit here is I'm switching at a very low frequency, so my switching losses are very low, right? My switching losses, turn on and turn off switching losses are very low, and I'm supplying an AC waveform. It's nice, it's great, but I have a lot of harmonic content, right? The alternative to this is to figure out a way to improve the harmonic. I mean, if you want to create a nice sine wave, you have to figure out a way to create the sine wave, and it's not going to be by switching at fundamental frequency anymore. You have to switch faster to be able to chop up this waveform in a way that it would make it resemble as a waveform that has less content, less harmonic content. So initially, so now we started with this simple 4-switch inverter, and we're operating the switches at fundamental frequency. And we're getting, and this is my 50 hertz, this is my 20 milliseconds. If this is a 50 hertz waveform, this is V input, and this is minus V input. Am I going to be able to run my load? Yes, I can. If I connect a heater, is it going to bother the heater? No. The heater will not be bothered at all. If this is my voltage waveform, I have a resistor. I have the current waveform will look exactly the same, and which means I have what? I have voltage harmonics and a corresponding current harmonic. Voltage harmonic corresponding. That means I will be able to transfer full power. I will not be losing power. Remember when we were talking about harmonic losses, it was because I have a sinusoidal voltage and distorted current. In that case, I have pure sinusoidal voltage at the fundamental frequency, and then currents at the fundamental, and many others. That many other stuff will not count, because the power is equal to V times I at a certain frequency times the cosine angle between them. If I don't have V's at the rest of the I's frequencies, then it's useless. Then all of these other currents are not helping me deliver real power to the system. But here, it's a square wave voltage. If I have a resistor, square wave current, no problem, life is great, right? But if I have an RL load, the current will not look exactly like the voltage. So I will have there will be some content in the current waveform that is not in the voltage waveform. So I will have some losses there. But assuming it's a resistive load, then this is perfectly fine. The problem is it has a lot of harmonic content. This is something that exists. And if I have an RL load, having a lot of harmonic content means that I have losses. I have current harmonic components that are not contributing to real power transfer, right? So for a resistive load, no problem. It doesn't matter. This is fine. Put a heater, yeah, it will operate as good as anything else. Put an RL load, any other real type load, then you will have a current waveform that will. How will the current waveform look here? RL load. How will an RL load look in this case? I'm putting this voltage across an RL load. What will the current look like? Again, assume it's an inductive load, okay? Assume it's an inductive load. If it's an inductive load, what will the current look like? A ramp. Where is the maximum value for the ramp? Here. Where is the minimum value for the ramp? Here, or also here, because I'm periodic, right? So it's a ramp if it's a pure inductive load. How about if it's not a pure inductive load? It's an exponential. So the exponential, it will look like this. It will look like this, right? The harmonic content in this blue waveform is not equal to they're not equal. I mean, this is a square wave. This is the Fourier series for the square wave. We just saw it, right? We just saw that it's V maximum over pi and then all the triplet harmonics. First, third, fifth, so not triplet, first, third, fifth, seventh, etc. So that's the Fourier series for the square wave. Is that the same as the Fourier series for this waveform? No. They will have some harmonics that are in phase. So they will have maybe the fundamental. They may have a third. They may have a fifth. But definitely, this square wave has transitions, significant transitions here. That means that there's a lot more harmonic content in these transitions, fast transitions, than this slow transition. There's a difference. I don't have the Fourier series for this blue waveform. But since the waveforms are not identical, then there's a difference between the harmonic content. That's the basics of just by looking at the waveform. If that's the case, that means I have some voltage harmonics that will not find a corresponding current harmonic at the same frequency, and hence will not be able to transfer real power. Is that good or bad? Bad, because I want to deliver AC power to my load. But I have current flowing that is not contributing to P equals V times I cosine phi, which is, these have to be Vx, Ix, same frequencies. If there are currents that are not at the same frequency, then it's useless. I'm not contributing to real power, right? So what do we want to do? We would like to be able to improve the load will not change. So the current is sort of dictated upon us, right? The current is going to be dictated by the load, right? You put a voltage, you create. So ideally, I would like to go and be able to create a nice, beautiful sine wave. That's ideal, right? But before doing that, people developed this in stages, right? So first we had this 4-switch inverter operating at the fundamental frequency of the output. Then, what's another capability I can do with, so this I'm operating either 1, 2, I'm operating either 1, 2, or 3 and 4 together, right? Either 1, 2, or 3, 4. 1, 2, or 3, 4. So it's either Vin or minus Vn, Vn or minus Vn. What's some other option we talked about last time for operating this inverter? I can get Vin minus Vn, and what else can I get out of this inverter at the output here? 0. If I turn on 1 and 4, or I turn on 2 and 3, I can get 0. So let me show you this. So would this be closer to a sine wave or not in harmonic content? This is a square wave with a ton of harmonic content, right? This is another waveform. I've added a 0 here. What does a sine wave look like? A sine wave looks like this, right? Sine wave looks like this, right? There's a huge difference between these two here, right? A huge difference between these two here, right? The closer the two waveforms are together, that's from a physical perspective. You agree that if the waveforms look close to each other, that means probably their harmonic content is similar, right? So now I have something that looks very different at many places here. So I'm trying to get closer to that. So here I add some 0 here and some zeros here, zeros here and zeros here. I'm a bit closer. So you would expect that the harmonic content in this waveform would be less than the harmonic content in the square wave, right? So people went on a little bit further. We will look at the equations for all this, but so they started with this, then added zeros. Then, okay, they realized that this is a nice trick to play with. If I add some zeros here and control my pulse width. If I control my pulse width, they realize, okay, it's interesting. I can get better harmonic content. Fine, I have to raise this value of voltage, right? Because if I want to meet the same RMS value, I will have to, of course, raise this. But they found a nice trick. So people said, okay, how about I do this? Maybe I do, instead of 1 pulse, I do 3 pulses. I do a small one here, a bigger one, and a small one here. And maybe I do this, and I do this, and I do this. Does this look closer to a sine wave or not? Here, instead of, rising suddenly, like, this is a 0 and then a sudden rise in the value here. Here I have, okay, it's like a sudden bump in the average value of the waveform, and then another bump, but with a bigger duration, right? So it seems it's closer to a sine wave, which rises in value, it rises slowly to a higher value. So here it has a small, this area would have a small average value, this area would have a higher average value, small average value, then 0, right? So you're closer to a sine wave, right? So people used to program this. They call this programmed pulse width modulation. And then they developed better techniques to become, so they found this trick of adding pulses helps. So they realized, okay, how about if I add many, many pulses? So how do I add that to make it as close as possible to a sine wave? So we'll stop here. We'll talk about this next class. So good luck on the exam.